Good morning everybody, and today actually I'm going to start the quantum mechanical aspect of paramagnetism. In the last my video I have given the paramagnetic property and the paramagnetic parameter, the parameter which explain the paramagnetic behavior of a material, which is known as mu and susceptibility chi symbol. That's what I have already calculated. Now how we can analyze the paramagnetic behavior of a material using the quantum mechanical aspect, that is very important. Why so important? Why study of magnetic behavior of a material is important? Because the magnetic material is a highly demandable in nowadays technology, and magnetic material used everywhere in medical science, in computer information technology and memory device, and that is why we have to analyze the magnetic behavior of the material. Okay, and it is very important as per demand. And second point second point is in some material, suppose this is a material, in some material it has inherently acquired some magnetic behavior. I means this material, suppose this is a material, this material already may have some inherent magnetic property, but in some material they initially do not have magnetic behavior or magnetic characteristic, but after application of magnetic field it will acquire the magnetic behavior and also retain the magnetic behavior. For example, hysteresis, you have studied hysteresis loop, and we apply magnetic field over a material, and we will analyze how much magnetic behavior acquired by the material. That's what I am going to analyze. I am not going to give you again the same thing that whatever I have told in the previous video. Okay, so magnetic behavior, we have a magnetic property. Whenever we apply a magnetic field over a material, we always change in energy take place. Change in energy always explain mu dot b, mu magnetic moment. Okay, this is not permeability. Okay, this is the magnetic moment, and this is the applied magnetic field. Due to applied magnetic field, the magnetic moment of a material, okay, magnetic or dipole, magnetic moment is associated with the dipole. Okay, dipole will try to interact with the magnetic field. As a result, energy level will get changed, and because of this energy, the magnetic moment is acquired by the material, and as a result, finally we get the susceptibility of the material. Susceptibility indicate the magnetic property, how much magnetic behavior it acquired after removal of a magnetic field. That's what I am going to study. Okay. So, so we have already in ACS we have already studied energy in magnetic field minus mu dot b. This is the interaction of magnetic moment. You can say this is the interaction energy of magnetic moment with magnetic field. You can say the interaction of dipole with the magnetic field. As a result of interaction, energy level will get changed, and because of which magnetic material acquired a magnetic behavior. Magnetic behavior means orientation of polarization, orientation of dipole along or opposite direction of magnetic field is known as the magnetic moment. Now, if we understand the magnetic behavior, then we have to look back the quantum mechanical how magnetic moment, spin orbit. There is a two magnetic moment. One is magnetic moment mu L, one is mu S. Okay, two magnetic moment is there. One associated with orbital magnetic moment, one is associated with the spin magnetic moment. So, in order to understand this two parameter, we have to look back some quantum mechanical relations from the quantum mechanical aspect. So, for example, in hydrogen atom, suppose you have already done why I am giving this example, so that most of the students you have already studied the hydrogen atom, Zeeman effect, normal Zeeman effect, anomalous Zeeman effect. So if we come from that point of view, then that point of analysis, then we can easily understand the paramagnetic behavior in hydrogen atom. For example, hydrogen atom, what happened? Hydrogen atom, this is Hamiltonian, this is H naught, this is HFS or spin orbit interaction, and H Zeeman. So this is the, suppose this is a hydrogen atom. This is a hydrogen atom. This is a system of hydrogen atom. Suppose consider this a hydrogen atom. Hydrogen atom, you have already one electron system. Suppose you apply a magnetic field. Apply a magnetic field over the hydrogen atom. Then what happened? The Hamiltonian of hydrogen atom. This is original Hamiltonian is C. Original Hamiltonian of hydrogen atom is P square by twice m. This is kinetic energy minus E square by R. This is the original Hamiltonian of the system. Now, after application of magnetic field over the hydrogen atom system, the Hamiltonian gets changed. This part is after application of magnetic field. Okay. Then we have to calculate the energy of the hydrogen atom after application of magnetic field. This is known as a perturbation. There is a 2-3 analytical theory. This is the original Hamiltonian. This part is introduced after due to application of magnetic field. Due to application of magnetic field, original Hamiltonian of the hydrogen atom gets changed. This is known as a spin orbit Hamiltonian. This is a Zeeman Hamiltonian. Okay. This spin orbit, this time, this Hamiltonian part arises due to spin orbit interaction, and this part is arises due to interaction of magnetic moment with the external magnetic field. Okay. Now we have already studied this part. I am removing here. We have already studied 3 analytical method. We have analytical method, or you can say approximation method. No need to write analytical method, approximation method. We have studied 3 approximation method. One is perturbation theory, 2 variational principle, 3 WKB approximation. Okay. We have studied in quantum mechanics. We have studied approximation method, perturbation theory, variational method, and WKB approximation. Now, what happened? Out of this theory, approximate method, what theory we will going to apply? That is based on the condition. Now, what is the condition? Perturbation theory you can apply to finding the energy of the system after application of external factor. External factor means, suppose if we have a glass of water, okay, if we drop a piece of stone, then whole system will get disturbed. Then after disturbance, after dropping of stone on inside the water, the energy level gets changed. So change in energy, if we want to calculate, then we have to apply the approximation. Now condition 1, perturbation theory you can apply only when if you must have idea about the original Hamiltonian of the system. If we do not know original Hamiltonian of the system before application of magnetic field, okay, original without application of external factor, original Hamiltonian of the system, you can apply perturbation theory. Okay. Suppose to me you don't know H naught, original Hamiltonian you don't know of the system. Suppose I have a system, I don't know the original Hamiltonian of the system, then I cannot apply this theory. Okay. Then we can go for variational and WKB method. But variational method required, you must have, if you don't know the original Hamiltonian, it's okay, but you must have some basic idea about the ground state wave function of the system. Okay. Ground state or first state, second state wave function, you must have some idea. Okay. For example, we know the wave function particle in a box, this formula, sin nx by L, this is A or X, this is the formula. Suppose if I write wave function A, x into x minus L, this is also wave function of the particle in a box, because when x equal to 0, the wave function is 0. When x equal to L, wave function is 0. That means this satisfy the wave function of particle in a box. In that case, if you have some idea about the wave function, ground state wave function or excited state, then you can apply variational method. If you do not have idea about ground state wave function of the system as well as Hamiltonian, then you have to apply the approximation method. Okay. Now we have a basic idea about the ground state wave function of a hydrogen atom. ground state wave function, Hamiltonian of the hydrogen atom. Then, so we are going to perturbation theory. How to calculate the perturbation energy? You see, perturbation energy is calculated. This is calculated. This is the energy of the system after application of external magnetic field. Okay, we always calculate it in quantum mechanics like that. Clear? So this is the wave function of hydrogen atom. Remember, three-dimensional hydrogen atom. I am not going to write that because this I am not going to cover this whole part. So we have to write H naught, sorry, psi n, H naught, psi n. This part expectation value. This is the first order perturbation. Psi n is Fs psi n plus psi n is Z psi. This is how we calculate. And this is this first term will give you original hydrogen atom, original energy of hydrogen atom. Second part give this is spin orbit interaction term. Third term is give minus mu L dot B plus this is magnetic vector form minus mu S dot B. Okay, this is the energy, and this energy is the original hydrogen atom energy, which is equal to E square by twice A naught N square plus this is L dot S. This is known as a spin orbit interaction term. You can say fine structure energy. Okay. L dot S means spin orbit interaction, and this part is known as the Zeeman energy. Zeeman energy, mu L dot B minus mu S dot B. This is Zeeman energy. This part is the Zeeman energy. Okay, this part will taking account the paramagnetic behavior of a material. That is why I am going to focus this part. Okay. And this is a hydrogen atom ground state energy. This is original energy means E n naught equal to, we often write E square by twice A naught N square. You can say this is minus is there. You can say also 13.6 electron volt divided by N square. We write normally like that. Okay, this is the original energy of hydrogen atom. My main focus is this part. This is my main focus part. Because of spin, because in a system, what happened? Suppose this is a system, I will apply magnetic field, I will remove the magnetic field. After removing the magnetic field, I will analyze the material, how much magnetic behavior of the material, how much magnetic behavior acquired by the material. That's what I am going to study. That's why I am focusing on this part. Third part is important part. Okay. Now, so in that case, I am writing again this term. So original energy of hydrogen atom. This is a perturbation energy. This is original energy. Original energy E square by twice A naught N square plus A L dot S spin orbit. This is the fine structure parameter, fine structure term, and my plus minus mu L dot B. This is the interaction of magnetic moment with orbital magnetic moment with external magnetic field, and this is a spin magnetic moment with the external magnetic field. This part I have focused on that part. Clear? I will focus specifically this part, and this part is known as a Zeeman energy. Remember, Zeeman energy, and in this term they associate with the normal Zeeman effect and anomalous Zeeman effect. If we know clearly what is a normal Zeeman effect, what is an anomalous Zeeman effect, then you can easily understand the paramagnetic behavior of a material. Okay. So energy term. Now I focus on this part, this Zeeman Z part, this part. This is a Zeeman energy. So for case one, you see carefully. Okay. So I will spin orbital energy. This is I level as the E1. This is the level as the E2. Okay. So first energy I will going to calculate E1 energy. So E1 equal to minus mu L dot B. Okay. Mu L, you have atomic physics and quantum mechanics, and you see this is already given in chapter 9 chapter 9 Zetili and Zetili book, chapter 9 and Zetili book, around 480 to 486 page. You check it. Okay, this formula is given, normal Zeeman effect, anomalous Zeeman effect. Now, now mu dot f you have in quantum mechanics or atomic physics. If we see the atomic physics Rajkumar book, and you will find L equal to how much? E by minus E by mm twice m L factor. Have you seen this formula? E equal to, I am writing again, L is suffix E by twice m L factor. This is the formula in atomic physics. Similarly, if we find the magnetic moment due to spin, it will be you can write it is it will be E by m S factor. Is it okay? This is you can find in that part in the atomic physics book, or if you see the chapter 9 of Zetili book, around 480 to 486 page. If you check it, you will find this formula. Okay. Now, if I put this value, then what is the value of E by twice m L dot B? Okay, B is a magnetic field vector. So L dot B means what is? And I can introduce another term. You can easily understand what is the value of ZL, E by twice m L dot B means L cos theta into B. Is it okay? L cos theta means Lz, third component of angular momentum. You will find in a quantum mechanics also book, chapter number 4, 5. Okay, 4 or 5 you can find it. ZL equal to 1. ZL is a gyromagnetic factor for orbital. It is equal to 1 constant, and this become Lz. ZL E by twice m. This is Lz B. Now, sorry, this is a Hamiltonian part. This is a Hamiltonian. If I write H1, or you can write energy, no problem. No problem. Hamiltonian means energy. This is the original Hamiltonian. Okay. So Lz means, if we take the value of Lz, if we take the expectation value, normally we write this is H1. If you confuse, we never confuse. That's why sometimes we replace H by En or E by H. Hamiltonian means total energy. So this is eigenenergy. So energy value E1 equal to expectation value of this part. So expectation value of this one. This one you can check it in page number 280 page. Chapter 5 in chapter 5 of Zetili book. You can find this formula. Okay, Lz equal to ml is cross. Okay, ml is cross. You always find this formula Jm equal to how much into J plus 1 is cos square Jm J square. Similarly, Jz is also Jm equal to this formula. I will tell you later. So expectation value, I will remove this part. Whole part I am removing. Expectation value become, this is equal to ZL. This equal to Lz equal to mh cross. So E is cross by twice m ml b. Okay. So E is cross by twice m. This factor is equal to mu b. So ZL equal to 1. You can put the value ml. This part mu b b. This is the energy due to. This is the energy due to the orbital interaction of orbital magnetic moment with the external magnetic field. This is okay. Now this this becomes, so total energy in that case, if I am not considering this part, okay, I am considering here. Why not consider? Because in this case S equal to, I consider 0. Spin of electron is not considered. I assume the spin of the system is 0, and then this term will exist. This is S. This term will exist only, and this is energy. And this is known. This is known as a ZL ZL is 1. If you don't want, you no need to write ML mu B B. Okay, this is known as a normal Zeeman effect. Normal Zeeman effect. Spin is normal. Okay, this is known as a normal Zeeman effect. Under this condition, total energy of the system E square twice A naught N squared plus A L dot S plus ML mu B B. This is the total energy of the hydrogen atom system after application of magnetic field. Okay, and this energy is known as a Zeeman energy. Normal Zeeman effect. Why it is normal? Because magnetic field is weak. Number 2, spin is not considered. Now, what is the possible value of M? Okay, this is I am writing here again so that you can understand without any confusion. So normal case 1 is known as a normal Zeeman effect. Normal Zeeman effect. Normal Zeeman effect, energy of the system becomes this one, E squared, and that's what I am not going to write. So E1 equal to, sometime in books del E it is written as del E, no, do not confuse, okay? Del E equal to, then you will write del ML, okay? Mu B, B, whatever it is written. You can write like way, or you can simply write del equal to ML mu B, B. So this is the energy of normal Zeeman effect. You have studied in atomic physics as well as quantum mechanics. Now what is the value of ML? ML take value minus L to plus L including 0. Remember, including 0. So total number of value twice L plus 1. This is known as the degenerate state. Degeneracy of normal Zeeman effect is twice L plus 1. Okay. Normal Zeeman. Clear? So remove this part again. Remove this part. Okay. Now selection rule in normal Zeeman effect. This is not related to paramagnetic. Yet I am giving the basic idea so that you can easily understand the paramagnetic. Selection rule. Normal Zeeman effect. Normal Zeeman effect del M, or you can simply write as del M or ML is equal to 0 plus minus 1. 0 to 0 not allowed. Remember. Okay. And you see energy level under normal condition is equally shifting. Okay. Degeneracy of twice L plus 1. That means, what do we mean by degeneracy? Degeneracy means its level is equally split into equally spaced energy level. Okay, that is known as the degeneracy. So one example, this is a selection rule. So one example, if I give you another example, then you can understand. I remove this part. Normal Zeeman effect. So again I am using case 1, normal Zeeman effect, normal Zeeman effect. So what is the energy equally spaced energy? Suppose one spectroscopic term. Suppose two. I'm giving an example of sodium atom, which comes in the net exam. Okay, this is sodium 11 atom. This question comes in the net exam. So there is a two D1, D2 line. One is a 1s half, and another is 1 D2 half. Okay, this is a spectroscopy sodium D1 and D2 line. So okay, sodium suppose D2 line. For this I am considering this one. How you have to calculate the energy, because this part is related to the partition function. You have to calculate partition. They will say that a system of electronic system is placed in a magnetic field, and it will interact with magnetic field and calculate the partition function. then you have to know this one. Suppose D1 line, how will spectral the LS notation? LS notation, you know LS notation, twice S plus 1 LJ. This is the LS notation. So D here D equal to L equal to 2, you know this value, and J equal to 2. Clear? Now number of level and S equal C. This term represent twice S plus 1 equal to 1. That means S equal to 0. That means from this term you can say that this is a normal Zeeman term, because S is not 0 or S is equal to 0. Spin is not considered, means it is normal Zeeman effect. Okay. Now number of energy level if you want to calculate for partition one, number of energy level is equal to twice L plus 1. L is equal to 2 into 2 plus 1. This is the number of microstep, because this will require, suppose you want to calculate K, L and omega. Omega means this one. Okay, number of microstep. Then you have to easily calculate the entropy of the system also. Now number of energy level will get shifted, 5 energy level will get. Okay, 5 number of energy level will get selection. Total number of state I am writing here. Number of energy level equal to twice L plus 1, which is known as the degeneracy, or number of microstate. 2 into 2 plus 1 equal to 5. So what is the value of M? Now you have to find the value of M. Value of M equal to twice L plus 1 value minus L2 plus L including 0. Okay, including 0. Now what is the value? Minus 5. L equal to minus 2, minus 1, 0, 1, 2. This is a 5 value. Now you have to calculate the energy. Energy, what is the formula? ML mu B B. Mu B means Bohr's magneton. Okay, which is equal to E squared by twice M. Is a constant value. So only value magnetic field is also constant. So first of you have to calculate the energy level. E1 means E equal to minus 2. You put the value of minus 2. So minus 2 means this will be minus 2 mu B. Then minus 1 mu B. Okay. Then E0 0. Then E1 equal to mu B. E2 twice mu B B. Okay. This in exam what happen, whatever exam NET get whatever they will say like that. Electronic system placed in a magnetic field. Okay, it will split the energy level. Suppose spectroscopic term 1D to calculate the partition function of the system. Then you have to calculate the number of energy level first. Then you have to calculate what are the energy value E1, E2, E3. Suppose this is E1, E2, E3, E4, E5. Then you have to calculate the partition function. From this partition function formula, you can easily calculate. It will become beta E1, beta ER. So in that case, this is number of energy. E to the power beta E1 plus E to the power minus beta E2 plus E to the power beta E5, 5 energy. So you put this value E1 equal to this one, 2, 3, 4, 5 like this. You can calculate the partition function, no problem. Now what happened? This is we will get the total number of. I have removed this point. E1 minus 2 equal to minus 2 mu B. E minus 1 equal to mu B. E0 equal to 0. E1 equal to mu B. And E2 equal to 2 mu B. Clear? So energy level will get shifted like this. This is E0, okay? This is equal space. This is E0, E1. This is E1 equal to mu BB minus mu BB. Then twice mu bb, then 2 mu bb. Now you see, according to the Zeeman condition, energy level, this is the gap. Gap is how much? Gap is mu bb. This gap is mu bb. This gap is mu bb. This gap is mu bb. That means what? All energy level in normal Zeeman effect equally spaced. Clear? Okay. I am going to case 2. I am going to analyze the case 2. Case 2. Because time is running, I am simplifying. Case 2. Case 2, we are going to consider the spin 0. Now we have considered the L is equal to 0. L is equal, only spin part I am going to consider. Okay? Okay, no need to case 2. Simply case 2, we are going to consider the anomalous Zeeman effect. Anomalous Zeeman effect. Anomalous Zeeman effect. Zeeman effect. Defined by L is not equal to 0. S is not equal to 0. In that case, Hamiltonian, due to the Zeeman Hamiltonian, which is introduced after application of magnetic field, is equal to, I can write mu bb, minus mu L dot B minus mu S dot D. Clear? Is it clear? This is a vector symbol, this is a vector, this is a vector. So I simplify, write mu bb H cross, okay, L plus Lz plus twice Sz. I can write. Okay. So this equal to mu bb H cross Zz plus Sz. Is it okay? 1 Lz plus 1 Sz, it become a Zz equal to Sz. Now what is the energy? Energy, Zeeman energy, expectation value of this one. I don't need to write it, this is the expectation of this one is Zeeman energy. Mu bb H cross Zz expectation value plus Sz. Okay. This is the expectation value. What is the expectation value of here? I am removing this part. Have you studied this part in quantum mechanics? It is chapter 5. Chapter 5. ZL book 280 page. If you see, you will find this formula. J expectation value of Jz means J. You can write J M Jz J. Okay, we have to write like this. Oh, we understand. Or you can simply N L J M in hydrogen atom. N L J J. And we write like this equal to half Mj H cross. You know this formula. Similarly, if we calculate this as a value, you check this space. 280 to 286 space. As a value, we will find the value. We will find this value equal to J into J plus 1 H cross square and Jm J dot S Jm. This part is related to this part 286 and equal to Jm Jz. And this part is already given in 486 page. Okay, chapter number I think it is 9. Chapter number 9 you will find equal to if you solve this equation you will get J into J plus 1 J into J plus 1 minus L into L plus 1 plus S into S plus 1 Mj is cross. Okay, if you put this value here and Jz equal to Mj is cross. See, I am removing this part. Okay, this Ez equal to mu bb H cross mj h cross plus, if you put this value, whole value, plus j into j plus 1 minus l into l plus 1 plus s into s plus 1, j into 2 will come out, okay? 2 will come, 2 j into j plus 1 mj is cross. Okay, if I remove now, h cross cancel, so mj will come on, mu b is here it will give 1 plus j into j plus 1, 2 j into j plus 1 plus s into s plus 1 minus l into l plus 1. Okay, and this factor is known as the gyromagnetic ratio Gj Mj mu b b. This is known as the energy of anomalous Zeeman effect. Remember, this is the energy of anomalous Zeeman effect. Now, important point from here, important point you have to remember for calculation as well as for exam purpose. Exam purpose. One is a selection rule. Number one, selection rule. Selection rule mj, or you can say or del m mj, you can say like that, equal to 0 plus minus 1, but 0 to 0 not allowed. This is the selection rule in anomalous Zeeman effect. Okay, number two, the energy level split it into twice j plus 1 level. Okay, this is known as the degeneracy. Degeneracy in normal Zeeman effect equal to twice j plus 1. Okay, and number two, number three, mj take value minus j to plus j including 0. Okay, this is the minus j to plus j, that is twice j plus 1 value. Okay. Number three, number 4 point, in normal Zeeman effect all energy level will equally space, but in anomalous Zeeman effect the energy level will not equally space. It will determined by gyromagnetic ratio Gj. For example, suppose 2s half, 2p half. This is a two spectroscopic term. So if we calculate Z for this one, Gj, if you put this value, what is the value? S equal to twice s plus 1 equal to 2, s equal to half from here, and j equal to half. If you put this value, I think you will get 2. Okay, and if you calculate this value for here, I think you will get 2 by 3 or 3 by 2, something like that. I am not going to calculate, you just calculate. This value for s equal to half, L equal to 1, j equal to half. If you put this value in gyromagnetic ratio, you do different. For different, see, for this energy spectroscopic term, Z value is different means energy will become different. So that means in anomalous Zeeman effect, the energy level, total number of energy level, that is known as the microstate, is equal to twice j plus 1. All lines are not equally spaced. Okay, this is anomalous Zeeman. Now become, this is in case of anomalous. Now back to the paramagnetic theory. Paramagnetic, from what we can understand, what we understand from here is that, what we understand, the energy, what we can understand, that energy is Z mu b, b, mj. This is the energy in anomalous Zeeman effect. What we can understand, initially theory, we in magnetic field is equal to Z mu b b. This is the theory. Magnetic moment. This is simply write mu dot b. So what you can understand, magnetic moment. So magnetic moment equal to G mu b b. G mu b mj. Mj or mj? Sorry, mj. This is equal to this one. Okay. Magnetic moment is arises now. Now you can say, what do you mean by paramagnetic behavior of a material occur only if there is an unpaired electron. Unpaired electron. If the system, suppose a consider system, n numbers of particles. Suppose sodium 11, sodium 11 281. Okay, you can understand. So 281, all electrons are paired according to above principle. See, above principle. This is block 2 electron, this is 8 electron, something 2p, 2s, 2p. This is block 2, 2, 2, 2, 2. 8 electron, 2, 8 electron, 3. This part, and last 1 electron. Now this 1 electron here in case of sodium is unpaired. If the system composed of n numbers of atoms and each atom has an odd number of electrons, then this electron will give the magnetic moment. See, under this part, for this part, mj equal to delta mj equal to 0, sum of s equal to 0, sum of j equal to 0. Okay. You can check this. This is already given in many particle system in quantum mechanics jetty. Okay, only odd pair of electron will account the energy magnetic moment, and this magnetic moment interact with the external magnetic field. As a result of this interaction, any material can equate the magnetic behavior of the material. That is known as the paramagnetic behavior. So what we can understand, whenever you apply a magnetic field over any material, then if the system or if the sample or medium has atom like that, atom which has odd number of electrons, and then this material then equate the magnetic behavior. So magnetic behavior means it will in odd number of electrons interact with the external magnetic field. As a result, dipole will align the direction of magnetic field, and this will equate the magnetic behavior of the material. Magnetization means orientation of the dipole along the magnetic field. This is as a property of a material, which is known as the paramagnetic. Okay. Now I am going to give you one numerical problem that you better understand. I have some problem. Now in classical theory, you can simply write mu equal to z mu b by s cross into z. Whatever here you see mu b mj in place of mj I am writing j. So mu square equal to z square mu b square s cross square j square. J square, if you put the value j square into j plus 1 s cross square. So z square mu b square j into j plus 1. And this is third term is arises only unpaired electron if the system or if the system composed of atom that has an unpaired electron, then it will be non-zero. That means it will have a magnetic moment. If this system has a magnetic moment, means it will interact with the magnetic field, it will equate the magnetic behavior of the material due to external application of magnetic field. Okay. Now you compare the classical theory. Classical theory we have already analyzed n mu square is by 3 kT, or you can write in terms of n mu square b also magnetic 3 kT. So magnetization m by n equal to mu square b 3 kT. Okay, it is, you can simply see the 1 by T. This is proportional to 1 by T. This is a Q law, paramagnetic law. Okay. So susceptibility, no need to write this. This is the magnetic moment. Susceptibility. I have given. This is the susceptibility which measures the magnetic behavior of a material. Magnetic behavior of material is equal to limit h tends to 0 dm by ds. This is susceptibility measure, which is equal to proportional to 1 by t. I am not going to calculate. This is the paramagnetic property. So AC tends to 0, this dm by ds, what is the meaning of this equation? Meaning of this equation, change of magnetization due to application of external field. When H tends to 0 means we are removing the magnetic field from the system. We apply the magnetic field, after all at the end we remove the magnetic field, means magnetic field tends to 0. This is the meaning of this equation. So it is susceptibility of magnetic behavior is inversely proportional to the temperature. But this is in classical case. And this is in quantum mechanics. Quantum mechanics, you see this equation, magnetization equal to classical formula, this is mu b TKT. So it will be, if we place mu b, mu equal to how much? G mu b, G square mu b square, J into J plus 1 b TKT. So susceptibility is equal to similar formula, limit H tends to 0, H tends to 0, dm by ds, it is also proportional to 1 by t, but this constant term, if I put in constant term equal to constant, so here is also constant, here is also constant, C1, this is C2. So classical and quantum discrepancy is the classical C1 not equal to C2. That means classical description, classically paramagnetic acquisition of magnetic behavior by a material due to applied external magnetic field, not account the spin of the system. Okay, but quantum mechanics, it will consider the spin of the system and it will explain the paramagnetic susceptibility in terms of the angular momentum J, which arises due to odd pair of electrons. Okay, but there is no significant difference between quantum and classical, only difference in their constant value. Okay, both follow the same rule. This is how quantum mechanical view of paramagnetism can be explained. So last point I want to introduce, this final point is this parameter mu chi, this parameter measure the magnetic behavior of the material. High value of this value is highly magnetically polarized, means highly equate the magnetic behavior. Suppose susceptibility is negative, this is negative for diamagnetism, and positive means this is positive for paramagnetism. For very high positive means it is ferromagnetic. This is how we can analyze the material. So high susceptibility value means once we apply the magnetic field or over the system, it will quickly equate the magnetic behavior. Quickly equate the magnetic behavior means the dipole of the material will quickly interact with the magnetic field and quickly align along the direction or opposite direction, parallel or anti-parallel to the direction of magnetic field, and this is known as a magnetic behavior. Okay, clear? Thank you. I hope you understand, and next class I will discuss some partition function for paramagnetic. This is how we can understand the paramagnetic. This is very important. You have studied in quantum atomic physics, you have to study in quantum mechanics, you have to study in statistical physics. This is a common part. That's why I merged quantum mechanics, atomic physics and statistics. Okay, thank you.